let's look at this from not the like computational looking drawing, but a simplified drawing. So it's the same diagram. If I have ethene, and I'm going to ignore all the single bonds for now. So I'm going to ignore one of the single bonds here, the single bonds here. I'm truly just focusing on each carbon's p orbitals that are being used for bonding in the sp2 orbital. Every time we have something that bonds, the reason for that bonding is for stability, and stability means lower energy. So when they come together and bond to form the pi bond, and they share their electrons with each other, that is going to be lower in energy than where you started with. That's why that happens. And if you're talking about just 2p orbitals, remember for every atomic orbital that you have, you're going to get the same number of molecular orbitals, right? Because orbitals are conserved. So you learned that in Gen Chem. All orbitals are conserved. They don't just disappear, and they just don't, like some of you like to say, pop off and disappear. They're conserved. So if I form a molecular orbital and they form a bond, that's one that's going to be our only molecular orbital. So that has the electron. So it turns out it's the highest, but it's not always the case. And then we have one that's not that doesn't have electrons, and that's our LUMO. So that's what we call our pi antibonding, and the HOMOs are pi bonding. So there may be others, but in this case we only have 2p orbitals, so I'm only talking about 2 orbitals right now. There could be other orbitals, and we will see them as well, but in this case we're only talking about 1. So to kind of explain the stability of pi bonds from a molecular orbital standpoint, let us first draw the pi molecular orbitals of butene, so dibutene, so sorry, butadiene, sorry, and then we'll come back to this image. So let us draw the molecular orbital diagram for the p orbitals of butadiene. So if I have butadiene, and I'm talking about the conjugated one because that's what we're focusing on in class. And if I'm only talking about the pi bonds, because I'm simplifying this, so if I have 2 pi bonds, each pi bond contributes 2 p orbitals apiece, so a total of 4 p orbitals. So when I'm looking at the molecular orbitals, if I start with 4 p orbitals, I need to have 4 molecular orbitals. And because my molecule is linear, meaning it's straight, we'll see what happens when we're talking about rings later on. We can essentially assume that we have 4 different molecular orbitals for those pi bonds. Okay, so again, I'm going to ignore all the sigma bonds for simplicity's sake. And I know that each of the p orbitals for my pi bond, each one of them gives me 1 electron apiece, so that gives me a total of 4 electrons. So when I draw my molecular orbital energy diagram, whenever I have these linear molecules, I'm just going to draw 4 different energy levels. And the first level, because I have 4 electrons, I'm going to fill just like what you learned in Gen Chem. And that accounts for 2 electrons. Then I go to the next set. And so since this is the ones that are filled, we call these pi bonding molecular orbitals, and we call this our HOMO. Because these are empty, we call them pi star or the pi antibonding. And since this is the lowest one of the unfilled, we call it the LUMO. So there's not always just 2, right? If I had 3 pi bonds, for instance, that means I would end up having a total of 6 p orbitals. That means I would have 6 molecular orbitals, right? So you could essentially do that. Now, what do these look like? So notice that they're different in energy, and the reason for that is the lowest in energy is where all my carbons, and if you remember back to Gen Chem, we use colors to represent phases of your molecule. So the phases are where the molecules can constructively overlap. That's more of a physics concept. And so I'm going to use these colors to represent the p orbitals in the same phases. So the dark is one phase and the light is a different phase. So when all the p orbitals overlap with each other constructively, they look like this. And this is the most stable you can get. So it's going to be the lowest energy. So what other combinations of my orbitals can I have? I can have where they overlap, where half of them are, and so you see that there's some sort of symmetry, because symmetry is always going to help you with stability. There's going to be a breaking point where they can't overlap, so these will overlap, but these don't overlap. And this is a node. A node is a place, like I said, with no electrons can kind of move through. And this is what causes a higher energy. And so it turns out that as I keep going up, as I move up with my molecular orbitals, that we start having nodes being there. So you can't have the same combination, right? So once everybody's in phase, there's no other way of making them in phase, right? So they're all in phase. So what other combination can my molecular orbitals take? Now, if I go up, the next one is going to end up having 2 nodes. And so the most symmetrical way to do that, because the symmetry adds stability, is I end up with 2 nodes, so the middle ones overlap. And then when I go to my highest one, everybody has a node, right? So we see that we go up and up in energy. And so if I were to look at what this actually looks like as true molecular orbitals, not these like half drawings that I'm doing, you'll see my lowest molecular orbital, everybody's in phase like that. And then the next one, they're overlapping like this. So we can think of the 4 carbons going like that, and then 2 carbons, and then another 2 carbons. And these are in phase, and those are not in phase. And then we can see the same thing with the next one, where the middle ones are in phase, but the outer ones are not in phase. Oops, wrong color. Okay, etc. So we can, and then the highest one, nobody's in phase. So when we're thinking about our molecular orbitals, this applies now to also the stability. Now you see that when we're in the lowest one, where everybody's in phase, our lowest energy, all our p orbitals are completely conjugated, meaning they're completely overlapping with each other. However, we do know that we can still rotate around that single bond. So, and when you draw the resonance structures, one of your resonance structures, like you've seen before, puts a double bond here, right? And so from looking at it from the molecular orbital standpoint, we know that that double bond that we see here, that single bond that we see here is not truly a sigma bond, and it's not really a pi bond. It's something kind of in between. So our resonance kind of shows us that. But our molecular orbital diagram actually helps to explain that even more. So remember, all 4 of the molecular orbitals exist. They kind of are on the same molecule, but one of them shows complete overlap. One of them shows partial overlap. So we can see, in average, we're kind of like partially single bond, partially double bond. So there is a partial double bond character and a partial single bond character, just like what we see in our theoretical resonance. Remember, resonance is just a way of drawing electrons to show you what the molecular orbitals are actually doing, right? And so our resonance actually shows us this, but the molecular orbitals, which are how our electrons are organized and our orbitals are organized in our molecules, actually proves this, that one of our pi bonding is full overlap and one is partial overlap. So before we wrap up, we're going to review a way that we can make a conjugated diene. Basically, if you start already with a double bond, you can do an elimination. Or let's say you can do a double elimination, which I would say isn't necessarily the best, because you could also end up with an alkyne. But if you already have an alkene, you can do an elimination and get that. So that's actually how we can make dienes and trienes and so on, is by starting with one double bond and essentially doing an elimination. But let's talk about if you have electrophilic addition, where will your products go? So it turns out there is a kinetic and a electrophilic difference between the two things. A kinetic and a thermodynamic relationship between where your products are going to go. And I'll draw the mechanism for you in a second, so you can see how we got the two different products. It's actually very much related to what we did with alpha beta unsaturated carbonyls. But at lower temperature, we tend to get what's called a 1,2 adduct, meaning that I add first the hydrogen, because remember we always add it in the less substituted side, and then the bromine, so that's 1 and 2. And the 1,4 adduct is adding your hydrogen here, but ending up with your nucleophile in the 4th position, okay? And so there is a relationship between temperature and which product that you get. And remember, if something is at higher temperature and you're getting more of it, it means that that's probably a thermodynamic product, meaning that you're overcoming activation energy to get it. And notice that this double bond is the most substituted, so it's the more stable. And so getting this product is the more stable product. It's the thermodynamic product. But this one happens more at lower temperature. It's the kinetic product, and we'll go over that in just a second. So let's draw the mechanism really quickly. So one of them is kind of obvious because we've seen it before. HBr will be attacked. You add your hydrogen. I'm not going to draw it in because it's understood. And then your bromine can then attack that position, right? So one of your lone pairs. So what's the difference in the 1,4? So the 1,2, pretty straightforward. We can add it on whichever side is the least reactive. In this case, they're both pretty reactive because they're identical. But a difference comes in that looking at the resonance here. So this molecule has a resonance structure. So again, I'm going to use a different color to remind us where that hydrogen is. Remember, there are other hydrogens there. If we shift this over, we actually form a more stable resonance structure, right? So this is more stable, but it does take some effort to move that resonance structure over. So in terms of the alkene, this is more stable of an alkene, but in terms of having a primary carbocation is less stable. Even though it's next to the double bond, this one is a secondary next to the double bond. So in terms of the cation, it's less stable. The alkene is a more stable product. And so what will happen is once you get to a high enough temperature, we'll overcome the energy it takes to get that resonance. So in this case, our bromine can attack at that 4th position. So remember, we put the hydrogen already. We call that position 1. So 1, 2, 3, 4. And we get our final product with being the 1,4 adduct. So let's kind of wrap up talking about the energy diagram. So again, we start out all the same. Everybody's starting materials, all the same energy. And we can get our 1,2 adduct fairly easily, but the double bond is less stable. So the product is going to be higher in energy because the pi bond is less stable. It's less substituted, okay? However, once we add the proton on, we get this resonance structure, we get this intermediate, and we can draw the resonance structure of it. And this formation of the resonance structure is why we have the increase in activation energy here. That's what's making the activation energy for the nucleophile to attack next higher, because we are also doing a resonance structure. So if we add enough heat to overcome that change in resonance structure, then it doesn't really matter at this point anymore. If I open the playing field and say everybody can use a cheat sheet like you did on test number 2, then everybody has the same opportunity. There's no activation energy anymore. Then it's the most stable product that's going to form, okay? And so we saw something like that in the previous unit. And so just to wrap up really quickly, our last thing that we're going to talk about is pericyclic reactions. There's only one that we're going to focus on. The other ones, I want you to look at them and read about them in the textbook, but I'm not going to test you on tests about it, but I do want you to be aware of them because there's some very interesting things that they can do. But the pericyclic reaction is basically reactions that don't have any polar components, no ionic or free radical intermediates. They're just going to be reacting in a cycle, and our next video is going to focus on that.